Hi everyone, my name's Ylann, and I was the test organizer for the general test for BMT 2025. And today I want to go through a pretty interesting integral that came up on the BMT 2023 calculus test, specifically question 9, which asks you to compute this integral right here. And by all means, pause the video right now and give this a shot, and when you're ready, come back and I'll go over a solution. All right, so now that you're back, I'm going to say right off the bat that the solution I'm going to present is actually slightly different than the official solution. Specifically, the official solution goes about this integral by expanding out the binomial you see here and using a bunch of trig identities and algebraic manipulation to get at the answer. And that's a perfectly valid way to do that, to do this integral. However, the method I'm going to show you today is another perfectly valid way to do this. And also the methods that I'll show you kind of generalize to other kinds of integrals as well. So yeah, let's get started. So the goal of this method will be to rewrite the sine of x plus cosine of x term as just a single term, just something that's simpler than sine of x plus cosine of x, so that we don't have to expand out this binomial. So the question is, how do we do this? Well, maybe a first natural step would be to try to graph this function. What is sine of x plus cosine of x? So here I have some axes, and let's first graph sine of x. So sine of x looks something like this. It's not the most perfect graph, but hopefully it'll get the job done. And then we can graph cosine of x, which will look something like this. And then finally, we can sketch the sum of the two, sine of x plus cosine of x, which looks something like this. Again, not the most perfect thing, but maybe you can suspect something about the nature of this new function. And after a while, you might suspect that it's another sinusoid. And in fact, this is correct. At least we can try to manage something with this assumption, and maybe we get at something pretty useful. So if we suspect that this is a sinusoid, then we can represent this new sinusoid as some amplitude times sine of x plus some phase factor. So the question is, what is the amplitude and what is the phase factor if this new graph is indeed a sinusoid? And basically, let's tackle the phase factor first. So what is the phase factor of this sine graph? What is this term right here? There are multiple ways you can go about this, but here's one way. So let's see what happens if we extend this graph slightly into the negatives. The sine of x plus cosine of x curve extends this way. And you can calculate this point right here to be exactly pi over 4. Where it reaches 0 first on the negative side. So looking at this graph, we can see that from pi over 4 on out, this new graph right here looks like sine of x from this point onward, which means that this graph is exactly sine of x but shifted to the left by a factor of pi over 4, which means that the phase factor here is exactly pi over 4. Okay. So the question is now, what is the amplitude of the sine curve? And we see that the amplitude is whatever the height is right here, which seems to be where the height is at pi over 4. And if you plug in pi over 4 to sine x plus cosine of x, you'll get like a root 2 over 2 and then a root 2 over 2. And if you sum those together, you get square root 2. So this is our suspected sinusoid graph for sine of x plus cosine of x. And indeed, if you apply the sum of angles identity to sine of x plus pi over 4, and then you expand everything out algebraically, you'll get exactly sine of x plus cosine of x, which is amazing. Because now what we can do is use this expression and replace the sine of x plus cosine of x in here with this. So let's do that right now. All right, so I've now substituted in what we just got. So the sine of x plus cosine of x is now a root 2 times sine of x plus pi over 4. And now we can reap the benefits of what we just did. So first of all, we can distribute the power of 6 to root 2 and sine of x plus pi over 4. So if we distribute to the root 2 first, root 2 to the power of 6 is the same as 2 to the power of 3, which is 8. And then we can factor the 8 out of the integral. So we'll get that this is equal to 8 times the integral from 0 to 2 pi of sine to the 6th of x plus pi over 4. This is all well and good. And from here on out, you can go through the rest of the solution without doing what I'm about to do. But for the sake of not needing to write x plus pi over 4 every single time, I'm going to make a quick substitution that will just get rid of this. So first, let's do the substitution t equals x plus pi over 4. So I don't have to keep writing x plus pi over 4 in here every single time. So we'll get that dt equals dx. And the new bounds will become 2 pi plus pi over 4, which is 9 pi over 4. And the lower bound becomes just pi over 4. And we'll get sine to the 6th t dt. Again, this is not a very necessary step to take. You can go about the solution without having done this, but for the sake of just not writing so much, I'm just going to make that substitution real quick. But now what we have is this integral. And this one is in a much more recognizable form. In fact, this is a pretty nice exercise in and of itself. It's still pretty hard, but if you want to give it a shot, go ahead. This is actually a pretty good exercise. But yeah. So from now on, let's actually just deal with this integral by itself, and we'll just remember to multiply the result that we get by 8 later. All right, so let's focus our attention to this integral, the integral from pi over 4 to 9 pi over 4 of sine to the 6th t dt. And there are actually a lot of ways you can go about this integral. For instance, you can try using trig identities, or use substitution, or integration by parts. And the method I'm going to show you today is we're just going to use integration by parts. So to do this, remember that for integration by parts, we need something to differentiate, which we call u, and something to integrate, which we call dv. And as with the integration by parts method, we need to choose these two wisely. We need to choose something that's maybe easy to differentiate and choose something that's easy to integrate. And hopefully we get some nice result that comes out. So when I look at this, I see that basically anything I choose for u, it'll be okay to differentiate. We'll have maybe a chain rule going on with power rule, but all in all, it's not going to be that big of a deal. However, there are only a couple of options you can choose for dv, the thing that you're going to integrate. So let's try, say, the number 1 for dv and sine to the 6th t for u. So u times dv has to equal the sine to the 6th, which we have right here. So, but if you go about the usual integration by parts method, you'll see that once you integrate dv to t, and you differentiate sine to the t, and then you apply the formula, the result that you get is actually pretty ugly. So it might not be the best to try this version. Another option, and this is a much better option, in fact, is to integrate sine of t and differentiate sine to the 5th of t. And this is actually the correct way to do this. You could try to integrate sine to the sine squared t and then break it apart using double angle identities. But again, you'll get something like pretty ugly, and you don't want to do that. You should try doing this one first before you do that. So yeah, let's run the integration by parts method using these two choices and see where that gets us. So first of all, let's differentiate u. So we'll get du is equal to, if we apply the power rule, we'll get 5 times sine to the 4th t. But we have to remember the chain rule, and the chain rule says that we have to multiply by the derivative of sine, which is cosine. So that's our derivative. And then for the integral, we get that v is equal to negative cosine t. And remember that for integration by parts, we don't need any plus c or anything. Okay, so now we can apply the integration by parts formula. So remember, this is u times v, which will be sine to the, or negative sine to the fifth, t, cosine t, evaluated from pi over 4 to 9 pi over 4, minus the integral of v times du. Now, we're going to acquire another negative sign from the cosine t, so a negative and negative will become a positive. And so we'll get the integral from pi over 4 to 9 pi over 4 of 5 times sine to the fourth t, and then the cosine times cosine becomes a cosine squared. Okay, so this seems pretty okay. Right off the bat, actually, if you go ahead and evaluate this part, it'll actually cancel to 0, which is really nice. So all we need to worry about is the second integral. And at first glance, this looks pretty bad. But maybe we can remedy the situation by turning everything back into sine of x, or sine of t in this case. And the way we can do this is to use a trig identity, which will be to replace cosine squared t with 1 minus sine squared. So that hopefully we'll get an expression with only sine and it'll be nice and simple or something. So if we do that, we can distribute the 5 times sine to the 4th t into 1 minus sine squared t, and then we can split apart the integral. So the first thing that we'll get is the integral from pi over 4 to 9 pi over 4 of 5 times sine to the 4th t times 1. So let's just write that down. And then if we do the other term, we have 5 times sine to the 4th t minus sine squared, or times a negative sine squared, my bad. So all in all, that would be minus the integral from pi over 4 to 9 pi over 4 of 5 times sine to the 4th times sine squared is sine to the 6th. And here we are. This integral right here, if I factor out a 5, it looks like we're in trouble because this integral is exactly the same as what we started with. So it looks like we've gotten a loop. But actually we haven't. And this is the key part of this, of what we're doing here. Basically what we've done is we've shown that this integral is equal to this quantity, whatever this is just a number, minus 5 times the same quantity. Which, if you read it carefully, this is essentially just an algebraic equation. So if we let this, the quantity of whatever this integral evaluates to, let's just let it be equal to I, then we can say that this integral is equal to whatever this evaluates to minus 5 times I, because this is exactly the same quantity. So let's just write that real quick. We can factor out the 5 here, and we'll get 5 times the integral from pi over 4 to 9 pi over 4 of sine to the 4th t minus 5 times the same quantity I. And remember, this is all equal to I, which means that we can solve for I. And if we solve for I, we get that I is equal to, well, I mean, if you move the 5i over to the other side, you'll get 6i equals this quantity, which means that after you divide by 6, you get that I is equal to 5/6 times the integral from pi over 4 to 9 pi over 4 of sine to the 4th t dt. So the question is now, we've kind of kicked the can forward. Now, how do you evaluate this integral? And actually, this is a good exercise. What do you think we should do to evaluate this integral, given how we evaluated this integral? I'll give you a second to think. And, well, the answer is that we can basically just chain what we just did. We just kind of redo everything that we just did. But we don't have to write everything, because a lot of things will be repetitive. So let's try to analyze how each of the numbers in this expression came about and see if we can find a pattern. All right, so I've cleaned up the board a little bit. So we have that the integral from pi over 4 to 9 pi over 4 of sine to the 6th t dt is equal to 5/6 times the integral from pi over 4 of basically the same thing, but with a 4 instead of a 6. And we've essentially just simplified the expression down. And now all we need to do is evaluate signs of the same integral but with a 4 instead of 6. So the question is, how do we do that? But I hinted just now that the way you do that is essentially we do the exact same thing that we did to get from here to here, where we just replace every time we saw a 6 with a 4. So if you go back and do the same exact thing that we just did, but we just replace every time we see a 6 with a 4 and like change everything accordingly, what we see is that basically this number, whatever the power is right here, will appear as the denominator right here. And and then this number right here is always 1 minus this number. So this right here is, the 5 appears because it's 6 minus 1. And then the power always gets reduced by 2. So this thing went from a 6 to a 4, so it's 6 minus 2. Which means that, let's see what happens if we do this again. So we get that this is equal to 5/6, and then if we repeat the same calculation that we did to get from here to here, but with signs of the fourth t dt, then according to this pattern right here, we'll get that this guy must be equal to, well, in this case we have a 4, and since the 6 corresponds to the denominator, we'll have the denominator of 4, and then the 5 corresponds to 6 minus 1, so the numerator will be 3. All right, now this thing, remember, it's now times the integral from pi over 4 to 9 pi over 4 of sine, well, now that we decrease the power by 2, sine squared t dt. Now, again, you could evaluate this using standard trig identities. You use like the double angle identity. But why do that when you could just repeat the same thing again? So let's do that one more time. You have 5/6 times 3/4, and then if we repeat the same pattern again, we'll get times, well, the 2 is now in the denominator, and then we have a 1 on top because that's 2 minus 1, times the integral from pi over 4 to 9 pi over 4 of sine to the 0 dt. But sine to the 0 is just 1, so we can just replace that with 1. But this guy is a very simple integral to evaluate because it'll just evaluate to whatever the difference between the two bounds is, and that is just 2 pi. Oops. So this integral will evaluate to 2 pi, which means that we've gotten rid of all the integrals from this expression. So now it's just a straight multiplication, and if we do that real quick, these 2's cancel, and then the 6 cancels the 3 and creates a 2 at the bottom. So all in all, we'll get a 5 over 2 times 4, which is just 5/8 times pi. So are we done? No, not yet, because, well, we're almost there. Remember that this integral right here was not the original one. The original one was this one times 8, which means that all we need to do is multiply the result by 8 here, and then these guys cancel out. And so therefore, the entire integral, remember it was the integral from 0 to 2 pi of sine of x plus cosine of x to the 6th power. This integral evaluates to exactly 5 pi. And that's the answer. So, hope you enjoyed, hope you learned something new, and yeah, cool.